I would like to start by thanking Irfan for putting together this meeting and also congratulating you and the whole Berkeley team to this new center. I'm very honored to be here, and I'm very happy to be in this session of honoring John Clark for his achievements. I want to tell two stories today. The first one is in collaboration with John, where we've looked at two-level fluctuators. And in this case, it's the charge fluctuators using a single electron transistor. In the second part of the talk, I want to talk about scattering experiments on an artificial atom, or a transmon qubit, which we have placed in front of a mirror. And that is work in collaboration with Chris Wilson, who's here in the audience, and Yushun Hoi. The first time I met John, I think, was in 1985, so roughly a third of a century ago to measure time, as John usually does in his talks. This was in Copenhagen when there was a meeting, and I think John was having a sabbatical at that time. This was also around the time when the MQT experiments were starting to work, and I was really very fascinated about those things that Michel and John Martinez and John Clark were doing, and that was a great source of inspiration. So. We of course met at conferences over the years many times, but in 2008, John became an honorary professor at Chalmers, and so he spent some longer time there, and we started to collaborate on noise. And also, since then, John has been coming every August for a couple of weeks, and we've sort of kept up this collaboration and this work. And John has promised me that also next August he will come. In fact, not only John will come to Chalmers and Göteborg in August next year, but also I'm hoping that many of you can come to Göteborg in August next year, because we're hosting the LT28 conference there. So the take-home message here is, of course, the website. There's plenty of time until registration, but I would like to advertise this here. So coming then to my first topic, of course, we've had several talks about two-level fluctuators here, so I don't need to say that much about them. We have some model for a 2L potential here. And in the case of charge fluctuators, you often measure those with single electron transistors, SETs. And then if you only have one, which is strongly coupled, you see these typical telegraph signal. But of course, typically you have many of them. And then if you look in the frequency domain, an ensemble of those two-level fluctuators, each of them give you a Lorentzian, but if you put an ensemble together with many of them, you get a 1/f spectrum, and that's really the way that most people have tried to gain information about the two-level fluctuators to measure noise. So here I have a list of about 10 papers where this is the case, where people have tried to extract information about the two-level fluctuators. But it's really very annoying that we still don't know what they are. I think it's very promising that there's been some progress on the flux two-level fluctuators, but on the charge two-level fluctuators, there's still a lot of unknowns. So I think we really need new methods to understand the two-level fluctuators. And we heard from Gerd Schön here earlier today, one way of getting some more information by using a qubit coupling to a single two-level fluctuator, extracting much more information. And what I'm going to tell you about here today is how you can use step response to also extract more information than by just measuring noise. It's a little bit like this. If I have a two-terminal component and I give it to you and ask, what is this? You're only allowed to measure noise. It would take you a while to figure out if this is a PN junction, a diode, or a tunnel junction, or a resistor, or just a short. But if I allow you to apply a bias, you could very quickly find out what it is. So the point here is to let's apply some bias or let's affect the two-level fluctuators by an external field. So what we're doing here is that we have our single electron transistor up here. So this is the central island of the single electron transistor. We have two tunnel junctions. We have a gate over here. And of course, when we put on a voltage on the gate, we induce a charge on the island. Of course, there will be some two-level fluctuators in between the gate and the island of the SET. So, and that will affect the potential landscape of the two-level fluctuators. And some of those two-level fluctuators will then change if you apply a large voltage on the gate. So you may change it into a metastable state. And then after a while, this two-level fluctuator will then tunnel out here and go to the other state. So what does this look like if you look at the IV curve of the single electron transistor? Well, you're at a fixed voltage here. So the blue curve is where you have no charge on the gate. And the red curve is when you have half an electron on the gate. But of course, if you then put on a gate voltage which is very much larger, your current is going to oscillate like this. And what you do is you go from one charge to a very large charge, and in our case, about 500 electrons. And of course, you're going to induce a large charge on the island, but then there will be these two-level fluctuators that will jump over, and that will happen over a long time scale. And that will induce extra charge, so you will have a drift from this point here onwards, adding a few electrons to the total 500 electrons that you added from the beginning. And so this is what we have done, and what we see is that this slow TLF relaxation can go on for a day. So our procedure is really that we start by just waiting for 24 hours before we do anything. And then we apply this large gate voltage, about 10 volts, and then we measure this drift for about 20 hours. And you can imagine that you can do this under many circumstances, and the student can get rather tired when he has done this at a million different temperatures and a million different other conditions. And this is Arsalan Karberian who did this really heroic work. So what do you see? Well, in the upper plot here, you see the current that goes between two values. That's just the minimum and the maximum current of the SET. And at the red point here, we apply a step of about 9.8 volts to the gate. And you can see what happens is that, of course, you change something here, but that's very rapid, so we can't really capture that. But then after that, you see that the charge is increasing, and the current of the SET is oscillating, but it's going slower and slower. So what we do is we extract from this phase of this oscillation, we can extract the charge of the SET, and what you see is that first you have a relatively rapid increase, and then it goes slower and slower and slower. And in total, you add almost about 10 extra electrons from this very slow charge drift. Now, what's interesting here is that if you plot the charge as a function of logarithmic time, you can see that you have a pretty straight line here. So you have a logarithmic increase of the charge with respect to time. This is done at 30 millikelvin and on a substrate of oxidized silicon. Now you can, the first thing you can check then is, well, what happens if I don't have such a big voltage? I change the voltage, and that's what you see here for for 4 different voltages. And what you see is that this logarithmic slope here actually becomes less steep the lower your voltage step is. So you can define this logarithmic derivative here as this, and so I'm going to call that h here. And if you plot that as a function of the step voltage, you can see that the logarithmic slope is increasing linearly with the applied voltage or the applied electric field. Now, you can do this then under different circumstances. So here, if we start to look at the 2 first black traces here, this is the same sample, but one is taken at 30 millikelvin and the other one is taken at 2 Kelvin. And you can see that this slope is very much the same in the 2 cases. So temperature does not seem to have a very big effect on this. And that, of course, speaks against thermal activation of these TLFs, but rather in favor of quantum tunneling. Then you can change also to another sample. So number 2 here is another sample, but you see that here the logarithmic slope is pretty much the same. We can change to glass instead of oxidized silicon, and there the slope is still pretty much the same. We can also go to sapphire, and the slope is a bit lower, and also notably you see that the steps seem to be larger. So there's a number of observations here, and so one is that this logarithmic slope seems to be rather independent of the substrate material. It seems to be independent of temperature, at least in this temperature regime below 2 Kelvin. The fact that you have larger steps here in sapphire seems to indicate that the distance you jump, the 2-level fluctuator is jumping in sapphire, seems to be larger than in oxidized silicon or glass. Moreover, you also see that sometimes so you have a general trend here going upwards, but in fact, sometimes it also goes down. So it goes in the wrong direction. So can we try to explain these things? And yes, we can. So if we model this, of course, we have a 3D system, but to make things easier to grasp, I've represented that in a 2D system here. But all the calculations later on have been done on the 3D system. So we define 2 fields. One is the gate field, which is the green lines here. So that's the electric field you get by applying a gate voltage. And then we also define a virtual field, which is the field if you apply a voltage to the island and then ground all the other ones. That's the black field you see, the black lines, black dashed line that you see here. Then the red dots here are the TLFs, and we're not quite sure if we have a volume distribution, the red ones, or if we have a surface distribution, the black one. But so let's leave that open for now. So one important thing is to figure out which of the TLFs will switch or not. And that's fairly easy because you have a starting energy difference in your potential landscape. And if your change due to the electric field is then bigger and in the right direction compared to this starting energy difference, then you will switch, otherwise not. And so that can be expressed by this here. So it's the gate field that controls which ones will switch or not. The other question is, if you switch, how much charge will you induce on the SET island? And that's given by this expression here, and that includes this virtual field. So these are relatively simple expressions that we can combine now. So we can actually make an expression for the total charge as a function of time, where we have this charge change per TLF switching. This determines which of the TLF switches, and then we have a probability of switching after the time t. And then we sum up an ensemble of those. We convert this into an integral, and then we get this expression where we indeed get this logarithmic increase of charge, as I showed you in the data. So this model does explain this, this logarithmic increase here. So this then has the density of two-level fluctuators per unit energy, per volume or surface area, depending on which distribution we have, and also per decade of time, because we only see a certain number of these two-level fluctuators because we only measure for a certain amount of time. So from this then, since we now have the time dependence of the charge, we can solve this logarithmic slope, and that we do here, and so we can extract this logarithmic slope under the assumption that we have a volume distribution, or under the assumption that we have a surface distribution. So from this we can actually extract the density of two-level fluctuators in the system if we have either volume distribution or charge distribution. And so what's interesting here is you see that what comes in here is a very simple expression. We have the density here, we have the electron charge, d here is how far you jump, which we take to be a nanometer. We don't know that, but it has to be a tunnel distance, so a nanometer is a good guess. And then what also comes in here is the scalar product of the virtual field and the gate field. And that we can then compute with finite element methods on the real geometry of our sample. And if we do that, we come up with these densities here that maybe do not tell you that much, but it's interesting to compare that to, there's some data from Kevin Osborne's group where they have looked at these densities of two-level fluctuators, and they have values which are quite consistent with what we get. On the other hand, if we assume that it's a surface distribution, we actually get numbers which are consistent with the numbers that came out from McDermott's group for these flux two-level fluctuators. So we still don't know whether it's volume distribution or surface distribution, but we have numbers that make sense at some level. Now, so one thing that we can extract from this analysis is that because we have no temperature dependence of the logarithmic slope, and because we have a linear dependence of the logarithmic slope on the step height, we can actually rule out that we have thermal activation between the two levels. And so, but it's fully consistent with having quantum tunneling, so I think that's really what we have. The other thing is that we can also, with this model, explain why the steps sometimes go in the wrong direction. That's because the charge is proportional to the scalar product of the virtual field and the gate field. And so if you look, say, underneath the electrode here, they go in the same direction. So that would induce one polarity of charge. If you're underneath the island, they go in the opposite directions, and then you would induce the opposite amount of charge. So this would explain why this goes up and down sometimes. Now, so this is my first summary of the first part of the talk. We measure the step response, so this is a new way of getting more information about two-level fluctuators. We see that the logarithmic slope of the drift depends linearly on the voltage step. It does not very strongly depend on temperature, and also not very strongly depend on material. So this rules out thermal activation, and we have been able to extract these these densities, but we can still not say whether it's a volume distribution or a surface distribution. Making more experiments with different geometries, we could probably extract that. So these are the two PhD students who made the work. And of course, we benefited a lot from John's experience of two-level fluctuators and just general knowledge of circuits like this. And
gave him a new name.
Sorry? Oh, sorry. There's some copy and paste there. I'm sorry about that, Martin. Okay. That brings me over to the second part of my talk, which is the atom in front of a mirror. And this is actually very related to the talk that Jeff Kimball gave yesterday. So this is placing an artificial atom in an open transmission line and measuring scattering properties of that using microwaves. And so, of course, what Jeff talked about was real atoms and laser light. But what we do here is we put a transmon qubit in an open transmission line, and then we can measure reflection or transmission. And in fact, a couple of years ago, we managed to show that you can have a very large extinction. So essentially, the qubit reflecting all the radiation and nothing gets through if you're at low enough power. So we measured an extinction of 99.6%. So you see, this is the transmission at very low power. It's practically zero, and then it goes up and reaches 1 when you go to high power. And the black line there is the theory. So there's quite good agreement between experiment and theory. So you can think of this at low power. You come in with a continuous field, which on average has less than 1 photon per unit time. And the unit time is the coupling between the qubit and the transmission line. So then the atom can reflect every photon coming in. If you go in and come in with very many photons at the same time, of course, you cannot reflect more than one at a time, and essentially all the other ones will pass by. Now, so then the interesting thing is to see what happens if you place this system in front of a mirror. And so what is a mirror? Well, a mirror is a piece of silver, right? So that is something that shorts the electromagnetic field to 0 at a certain point in space. And since we have now a one-dimensional space, this is just a short. So the short here is our mirror. So that's going to reflect the electromagnetic field completely. But then the electromagnetic field that we send in here can also be reflected by the atom, which is then placed a certain distance away from the mirror. And in this case, that's 11 millimeters. Now, you would like to be able to change the distance between the mirror and the atom. But of course, here it's fixed. But what you can do is you can change the frequency. So measured in number of wavelengths, you can change the distance between the atom and the mirror. So it means that you can change the mode structure so that you can be either at the node or an antinode of the electromagnetic field where you will have your atom. So this is the measurement setup. Here we send in a signal. We attenuate it. It goes through a circulator and meets the atom. Then we have a distance to the mirror where it gets reflected, whatever is not reflected by the atom. And everything goes back up here, and we can then measure that in this amplifier chain. And here is also a flux loop so that we can induce flux and change the frequency of the atom. So now, if we look at what happens, we see here that this is the reflection coefficient, the amplitude of that. And you can see that there's a dip here. This is when we go on resonance. And the reflection is partly from the mirror, that's this -1 here, and partly from the atom, which is this expression here. If we go to the low power limit, which we're going to do, which is what we are in this data here, you can simplify this so that it depends on the coupling rate or the relaxation rate and the decoherence rate and the detuning in frequency. So from this trace here, we can extract, in fact, both the relaxation rate and the decoherence rate. And of course, from that, we can also then get the pure dephasing rate. So that's what you see here in this. Now, here you see what happens as a function of flux. So when we change the frequency of the qubit. And you can see here that here we see this dip, but then there we come into a region here and here where we have a dark state, where we don't see the atom any longer. And that's, of course, when the atom is at a node of the electromagnetic field. So you can also compare then the line width here. So if you take the red arrow here, that's just before you go into the dark region, then you have a very narrow line width. And when you're down here in the blue arrow, you have the blue trace where you have a substantially wider line width. And so extracting from that, we can actually see that the relaxation time or the coupling time changes by an order of magnitude when we go from the red to the blue. And the reason is of course, that not only are we at the node for the signal that we're sending in, we're also at a node for the vacuum fluctuations that is coming from the transmission line. And if you lower the vacuum fluctuations, you lower the spontaneous emission rate. Now we can then also change the power that we send in. So then if we do that on resonance, we can simplify this expression in a different way. So here we have the relaxation rate, gamma 1, the decoherence rate, small gamma, and then the Rabi frequency of the radiation that's coming in. And what you see then is that you see reflection here at low power, you see reflection from the atom. And at high power, you see reflection from the mirror. And then there's this interesting point here where the reflection from the mirror and the reflection from the atom are canceling each other. And then, of course, you can answer, well, where does the power go here? And that is because we're measuring only the coherent reflection. So in fact, everything goes into incoherent scattering at precisely this point. And we can sort of quantify this point here at very low power and this point here where it goes to 0. So that from that we can also extract the pure dephasing rate divided by the relaxation rate. And you see, if you plot the real and imaginary part instead of the amplitude and phase, you see what's going on. The real part, the imaginary part doesn't do anything. It's really the real part that changes from positive to negative. So reflection on the atom up back here and reflection from the mirror here. Now, if you can measure the relaxation rate, you can in fact measure, or you measure the spontaneous emission, you can in fact measure the vacuum fluctuations. So we can use this to extract the vacuum fluctuations because the relaxation rate is proportional to the spectral density of the vacuum fluctuations. And moreover, this k squared here comes in also in the relation between the Rabi frequency and the input power. So from this point here, we can actually calibrate and measure this k value here. And so if we then convert our relaxation rates that we have measured into power spectral density of the quantum fluctuations, this is what we get. And the black line is what we would expect And so here at 1/2 L length over lambda, this is when we're at the antinode and where we in fact have canceled the vacuum fluctuations completely. So sometimes people say sloppily that you can't, the quantum fluctuations are always there and you can't do very much about them. But here you can actually interfere them away. But of course, you're only interfering them away at one single frequency. So at a different frequency, you would actually enhance the vacuum fluctuations. And that you see if you zoom out and look at the broader picture. So here, you're at a node of the electromagnetic field, and here you're at an antinode. So here you would actually have twice as strong quantum fluctuations because you have constructive interference. Okay, I end with this second summary here. We've investigated an atom in front of a mirror, and so we measured the lifetime of an atom, and we've shown that it can be modified by placing it in front of a mirror. And I've also shown that we can measure the strength of the vacuum fluctuations, we've been able to extend the lifetime of the atom by a factor of 10 by doing so. So the take-home message from this is that you can increase your lifetime if you look in the mirror. So this work was done by Yushun Hoi and Chris Wilson. The sample was made by Arsalan Pourkabirian, and the theory we got help from these guys in the group of Göran Johansson. And let me end by saying happy birthday to John, and thanks for all the nice moments we've had, not only from me, but also from all the friends at Chalmers who for different reasons could not be here. So thank you very much.
Thank you, Per. We have time for questions. Over there.
So, Per, if we would think along the fluctuation dissipation theorem, which maybe is not applicable here, but there should be a link between the relaxation you observe of the charge that you measure after this pulse and the amount of 1/f noise.
Yes, there should be.
And is there, what would be the connection?
In fact, we thought along those lines, and we tried to make a connection between the noise we measured and the step response. We were not able, so we got sort of ballpark right numbers, but we were not able to make it quantitative enough to put that in the paper. So, but if we make a more careful experiment, I think that should be possible to compare a noise measurement with a step response measurement. And that's really what we would like to do, yeah.
You said that charges are sometimes canceled, sometimes they increase because of the scalar product.
Yeah.
Does that depend only on the geometry of the device or on the material of the substrate?
No, that only depends on the geometry. So this is the difference between fluctuators moving underneath the island or underneath the electrodes. So those two ensembles go in different.
Why do you see it only on subsides?
If you look closely and you blow curves up, you can see it also in some of the other curves. So here, if you look, so this is the glass. Here you can also see that it goes, but it's just easier to see in the sapphire.
I see. They're big.
Yeah.
Winner. I'm wondering whether you can use the information about these step sizes to try and learn a little bit more about where the fluctuators actually are located. So could a reason that the steps are bigger on sapphire be that the defects are more closely situated to the metal film, and therefore does that work?
Yeah, that would be one explanation. Another explanation would also be that the jumping distance is longer for some reason in sapphire. And we would have to try more samples with different geometries to find that out. But definitely you could do histograms of these steps and extract more information. So the take-home message here is really that this is a new method to measure the two-level fluctuators, and that this would give more information.
Have you thought of any system to decouple volume versus surface?
So to do that, you would need to have different geometries with rather large SET islands and compare those with relatively, and also you would like to make sort of an easily computable. So it took us quite some time to calculate this scalar product and integrate it over the whole volume. So you would like to have an easily calculable geometry.
In the same spirit, Gert was mentioning defects in the barrier.
Yes.
Do you ever see them?
So we are quite sure that what we see here is not in the barrier, because the barrier is actually screened. So inside the barrier, you don't see the external gate voltage. Moreover, the densities are too small to fit that many fluctuators into just the barrier. So the ones that Gerd was talking about are not exactly the same, at least, two-level fluctuators.
But both have a high density. I guess you had also a very high density, wasn't it? 10 to the 24 per cubic meter.
Yeah, but you would not be able to get, if you only had the ones in the barrier. The barrier is not big enough to include all the two-level fluctuators we see here.
Yeah, so I was wondering if you can rule out single electron jumps and whether this was a normal SET or a superconducting SET, which is related to the first part.
So this was a normal SET. We applied a magnetic field of a Tesla to just get rid of that question. And what was the first part?
Can you rule out single electron jumps? Because it's periodic, I'm just wondering if there's something else in your data that would...
Oh, you mean that it could be sort of larger lumps or clusters of charge that would jump?
Well, I'm just wondering if it moved by one electron, then the characteristic is periodic. So is there something else in your data that rules that out?
Oh, but even if, the two-level fluctuator, we assume that you tunnel one electron charge. It might be an ion or something, but we assume that it's an electron, and that induces a very small charge on the island. So that induced charge is much smaller than so it's a percent or something or less of the electron charge.
One very short last question, perhaps. If that's not the case, we will reconvene here at 4, okay? 4 o'clock. Happy birthday, John, and let's thank all the speakers of this session.